In this video, I'd like to talk about some topics from Chapter 1.3 on the elements. What is an element? As we learned in the previous section, an element is a pure substance made of a single type of atom, and because of that, it cannot be broken down into anything simpler. Here is about the silliest question I'm going to ask this year. Where do we find the elements tabulated? Why? On the periodic table of elements, of course. And here is the official Edinburgh School periodic table of elements. This is posted as a PDF in the Chapter 1 and 3 topics box, and I would strongly encourage you to download a copy and print it if you like so that you can refer to it. We will be using this version of the periodic table throughout the entire year. Now, as you notice, each element comprises a box on the periodic table, and there are 118 of them. Let's ask ourselves, what information do we find inside each element box on the periodic table? Well, here's the box for one of my favorite elements, palladium. Palladium is a transition metal. It is very rare and very expensive, and it is used extensively in catalysis. What you see largest is the element symbol Pd above the name palladium. Pd for palladium kind of makes sense. Below, one normally sees the atomic mass, which for palladium is 106.42. We will talk later in this unit about exactly what that means and how that's measured. And in the upper right-hand corner, you see the atomic number. For palladium is 46. And as you may know from previous science classes, the atomic number is the number that uniquely identifies each element. Palladium is palladium because it has an atomic number of 46, and that is the number of protons found in the nucleus. And we'll talk about atomic structure later in this unit. Pd for palladium makes sense, as does C for carbon, N for nitrogen, O for oxygen, and so forth. But what you see is that some element symbols don't seem to match up with the name that we use. And that's because many of the element symbols are based on the ancient Latin or Greek names for the elements. Here are some fun examples. Sodium has the symbol Na because the ancient Latin name for sodium is natrium. Likewise, potassium, the symbol is K from kalium. Iron has the symbol Fe for the Latin name ferrum. Lead, this is one of my favorites, has the symbol Pb, which stands for plumbum, which sounds kind of like plumbing. Hey, guess what metal the ancient Romans used to make their water pipes? Lead pipes, hence plumbum. Silver has the symbol Ag from the Latin word argentum. Which South American country do you think has large deposits of silver? Argentina. And gold has the symbol Au from the Latin word aurum, meaning bright or shiny. There are many others, and we can talk about them in class if you're interested. Now, let's describe the periodic table. We see that there are 7 horizontal rows, which we call periods. We'll jump back and look at those. First, second, third, fourth, fifth, sixth, and seventh period. There are 18 vertical columns, which we call groups or families, and those are numbered sequentially from left to right, 1 through 18, as you can see at the top of the periodic table. The groups or families have names, and some of these I'd like you to know. Group 1 elements are called the alkali metals. The group 2 elements are called the alkaline earth metals. Groups 3 through 12 do not have names, but they are referred to as the transition metals. And if you jump back, you can see that groups 3 through 12, you're transitioning from the left side of the periodic table to the right side. Groups 13 and 14 have very boring names. 13 is called the boron group because boron is the element at the top. Group 14 is called the carbon group because carbon is the element at the top. Group 15 has a very unusual name. They're called the pnictogens. I don't know whether the P is silent or not. Group 16 are called the chalcogens. Group 17 are called the halogens. And group 18 are called the noble gases. The 4 groups that are in bold here, groups 1, 2, 17, and 18, I would like you to know the names of. In general, how is the periodic table arranged? In order of increasing atomic number. So we see we start with hydrogen, atomic number 1 in the upper right-hand corner, helium 2, 3, 4, 5, 6, 7, 8, 9, 10, and so forth. However, what you'll see is that at the end of a period, at the far right, we go back and start a new period so that similar elements are in the same column. We will learn in the next unit about why the periodic table looks the way that it does, but in general, elements in the same group or family have similar chemical or physical properties. Not identical, but similar. Whereas elements in the same period, that is, the same horizontal row, have varying chemical and physical properties, but one can generally say that the closer the elements are in the period, the more similar their properties, and likewise, the farther apart they are, the more different their properties. Every periodic table is set up in such a way that you've got these funny two rows of elements hanging off the bottom. Let's go back and look at these, starting with cerium and thorium. So the question is, what is going on with those? Those are called the rare earth metals, and as the name implies, they occur in the Earth's crust in extremely small amounts, and they are relatively reactive and soft metals. Some of them are radioactive, and all of those after uranium, atomic number 92, are synthetic, which means that they do not occur naturally, they were produced in a laboratory. There are two series called the lanthanides and the actinides. The lanthanide elements comprise elements cerium through lutetium, number 58 through 71. They actually fall between lanthanum and hafnium. So if we go back and look at the periodic table, this first row, 58 through 71, cerium through lutetium, are called the lanthanides because they follow lanthanum. Look at the sequence in atomic numbers. Cesium 55, barium 56, lanthanum 57. After lanthanum, we jump down to cerium, and from cerium to lutetium, the lanthanides. We then go back to hafnium, number 72. So these elements don't actually belong to a group. They are wedged in between groups 3 and 4, but they are in period 6. Below the lanthanide elements are the actinide elements. They're called the actinide elements because they follow actinium in the periodic table. And they are thorium, atomic number 90, through lawrencium, atomic number 103, and they fall between actinium and rutherfordium. So if we jump back to the periodic table, here we see francium 87, radium 88, actinium 89. Then we jump down to the actinides following actinium and thorium 90 through lawrencium 103. And then after 103, we jump back up to rutherfordium 104. And again, like the lanthanides, they do not belong to a group. They are wedged in between groups 3 and 4, but they are part of period number 7. Now, you may have noticed in the upper right-hand corner of the periodic table, there's a funny sort of staircase-like line that looks something like that. Okay? That actually is a boundary that separates the elements in the periodic table into 3 types or categories. These are metals, which are generally to the left of the line, nonmetals to the right of the line, and the 6 elements listed above are metalloids, which are those that are touching the line, with the exception of aluminum. Aluminum touches the staircase line, but it is not considered a metalloid. It is, in fact, a metal. So if we go up and look at the periodic table again, there's the boundary line. In general, the metals are to the left of the line, the nonmetals are to the right and above the line, and those touching the line, with the exception of aluminum, are considered metalloids. And let's talk about general properties of these 3 categories of elements. Metals are good conductors of heat and electric current, and we'll learn in Chapter 6 that that's because they have electrons that can flow freely. They are lustrous, which means they're shiny. Metals are malleable, which means that close to the melting point you can smack it with a hammer and flatten it out into a sheet. They are ductile, which means you can draw them into thin wires. Most metals are solids under normal conditions. The exception would be mercury, which is a liquid at room temperature. Nonmetals, on the other hand, are insulators. They are poor conductors of heat and electric current. In terms of physical states, many of them are gases, some are solid, and one of them, bromine, is a liquid under normal conditions. They have quite variable properties in reactivity. They vary from the completely inert noble gases like helium, neon, and argon that do not react at all, to fluorine, which is probably the most reactive element on the periodic table. Metalloids have properties that are intermediate between those of metals and nonmetals. Some are lustrous, some are slightly malleable, and almost all of them are semiconductors like silicon. If you haven't already done so, please go to the topics box or the class schedule and click on the link to watch the video on the properties of the halogens, which I think you'll find interesting. That's all.